everyone. Today, let's work on leetcode 1483, the Kth ancestor of a tree node. So this is a very classical problem, and I think if you haven't seen this problem before, and the chance you can solve it, especially during an interview, is very, very low. So let's see what this problem is about. So we are given a tree. The problem is pretty straightforward. You're given a tree with n nodes, and you are going to return the Kth ancestor. But you need to return that in an efficient way. So the naive approach is to store all the ancestors, but that will require a large amount of memory, and which will, I think it will exceed the memory limit for this question. So I think we'll just directly go to the solution, because if you haven't seen this problem before, it's very rare you can figure it out by yourself. So the key point here is to use an array. Let's say it's f, I, k, to remember node I, the parent, the 2 to the kth ancestor. Okay, so this is the key point. So that if we have, let's say, to get the mth ancestor, then m, for example, equals, the binary representation is 0, 1, 0, 1, 0, 0, 1, 1. So then we can just try to find out fi. So this is 0, and then we can try to find fi. This is 1, etc. Right? We can retrieve the mth ancestor this way. So let's see how we will write the code. So we'll define the vector called f, and also a vector called g. G is the graph. So f is initialized as -1 for each position. It has n nodes, and because the total number of nodes is let's see, it's 5 times 10 to the 4th. So the layer is at most 16, right? We just put 16 here, and all the value are initialized to -1. And this is g, and we first calculate g. So for int I equals 0, I less than, we call this parent, p size plus I. Then so at the same time we can calculate the root as well. So if pi equals -1, then root equals I. Otherwise, so g pi equals pushback I, right? Pushback I. So this g is gi is the list of child of node I. Okay, then we can have a queue to store to do the BFS. So basically we first add this root inside this queue, then we go to this node, and we put this node in the queue and this node in the queue as well. Then for this node we do the expansion. We put the 3 in the node, then 4 in the node, then 5 in the node, 6 in the queue. Okay, so queue push root, then we do the while loop, queue size and T is the first element in the array, and remember to pop the array. Then for int C is child in the GT, right? T is some node here, and C are all the child for this node. So the first thing is FC0 is equal to 1. I think it equals to T, right? Because the C's first step parent, 2 to the zeros, is 1. C's 2 to the zeros parent is T. So we have that here. Then for each position I equals 1, let's say k equals 1, k less than 16, plus k. If f c k not equal to -1, then f c k equals c k minus 1, right? Its parent is not, so this means it is not the root element. C is not the root. So f c k minus 1, k minus 1. Okay? So every time we go half of the step, we first go to 2 to the k minus 1 element, then we continue this process. So this is because C is 2 to the k minus 1 ancestors, 2 to the k minus 1 ancestor equals C is 2 to the k's ancestor, right? This equality will always hold. We first go k minus 1, 2 to the k minus 1 step. So we first go half, then we go up another half. Equals, we go directly to the to the k's ancestor. Okay. So, and don't forget to add this C back inside the queue. Push C. Okay. I think that's it for the constructor pre-processing. Then whenever we want the kth ancestor, we will just loop over the 16 bits. So if k right shift I and 1, then we say node will be equal to node and k, right? And I think this is I, right? We need to go I step. And if node is equal to -1, we just return. Then we return node. Let's see. So this is not comma. Okay, I think it will work. Let's submit. Okay, and I think it passed. The key observation here is when we try to go up 2 to the k step, we can first go half, then go up another half, so that we can use this matrix to represent for node I, the 2 to the kth ancestor information. And so I think that's it for this problem. Thank you for watching, and see you next time.